Good afternoon. So, we have come to the end of the semester's journey, which we began in July. We started right from probability theory and went on to explore various major classes of estimation problems, and in the last class we have also seen that there are many other types of estimation problems which exist. So, this class is to reflect back on what we did throughout the semester and review some of the major concepts that we learned, and then say goodbye for the examination. Let us review what we said in the first class. In the first class we tried to begin with a definition of what is estimation, and we said that we want to estimation is a kind of approximate calculation or of what, of estimation in I referred to a dictionary and said that if estimation is mentioned in the dictionary as approximate calculation or judgment based on available evidence. So, here when we talk about estimation, we are trying to calculate what? We are trying to calculate signals, or we are trying to calculate systems. That is why the course is called estimation of signals and systems. So, and we want to compute compute approximations of the signals. So, we are trying to leave out certain things. So, what are we trying to leave out? We are trying to leave out the noise in most cases. And if we talk about judgment, what judgment are we making? We are trying to generate from the information which is given to us in the form of measurements. We are trying to judge and generate several other types of information, in the sense that we are trying to predict, we are trying to find information what we can say about what is very likely to happen in the future, or we are trying to detect, we are trying to see that whether in some signal we are suppose we are given a signal which is mixed with another signal, whether we can detect whether a signal that we are looking for is present. We are trying to classify signals, in the sense that we are trying to see whether certain properties of the signal are present or not, and all this we are achieving through computation. We are also sometimes sometimes we cannot measure the exact signal which we are looking for. So, we are trying to see whether through computation we can get back the original signal. So, in other words, we are trying to compute some desirable information based on available evidence, which may contain various unknown, uncertain, sometimes undesirable elements, which we typically refer to as noise. And why do we estimate signals and systems? We estimate signals because sometimes measurement is not feasible, and or it is noisy, or the measurement is simply not available because we are trying to talk about the future. We estimate systems which are typically dynamic and complex, and all this, as we have seen in the course, that all this we are doing using models. So, this is what we said when we opened the course about estimation. At the end of the course, we can probably say many more things. So, I tried to look at estimation from various ways. First of all, remember that what are we essentially trying to do in estimation? Essentially, we are trying to compute values of signals. So, in that sense, it is like a sensor. What does a sensor do? Let us take a thermocouple or an RTD. if you put it in the process, it gives you the value of a quantity called the temperature, right. So, such devices we call sensors. Now, here also we are trying to sense various quantities. For example, from we have seen that from radar measurements we can, from radar measurements of position, we are trying to estimate acceleration. So, in that sense, in that context, the Kalman filter becomes a sensor for acceleration, right. So, we are not having any physical sensor here, we are having different types of physical sensors, but we are trying to essentially sense a variable. How we are sensing the variable? By using, in this case, kinematic models, right. So, that is why in a sense, for a large number of applications, estimation is nothing but model based sensing. Why do we want to sense? Why do we want to sense something? In many cases, obviously, when we are trying to sense, we are trying to get some information from the system. Why do we want that information? Because we want to take action, right. So, obviously, we do not take action open loop or in a predetermined fashion, but in many situations we take action which is based on the current behavior of the system. So, to be able to generate meaningful action, we need feedback from the system that we are trying to control or we are trying to operate, right. So, in that sense, estimation gives us feedback, but it gives feedback which is much beyond conventional sensing. I mean, as we have seen, for example, we have, suppose we are trying to probably you have seen the case of a tool condition monitoring case. That is, we wanted to find out, we wanted to sense to what extent a particular machine tool has worn out during its operation. Why do we want to know that? Because we want to decide when we have to change the tool so that our performance of manufacturing is not sacrificed. Now, for that we need feedback from the tool, and we need this feedback while the tool is working. So, we have seen that to get this feedback, we have to we can employ estimation, and in that sense without having any conventional wear sensor, we are able to give a feedback for this supervisory action to the operator, by which he can decide when to change the tool, right. So, in that sense, estimation lets you give feedback much beyond conventional sensing can. Estimation is also for a large number of cases, estimation is actually a classification problem for decision. For example, we have seen the case of fault detection and diagnosis. What essentially are we trying to do? We are looking at the signals and using estimation techniques, we are essentially trying to classify the dynamic behavior of the system into one of two classes, either normal or faulty, right. So, perhaps if we can get this decision, we can take very fruitful action, in the sense that we can, if we find that the process has developed a fault, perhaps we have to take a different course of action, perhaps we have to shut down the plant, we have to do many things. So, to be able to do all that, first of all, looking at the input output behavior, we have to classify that behavior as whether it is normal or whether it is faulty, and estimation becomes a tool for that classification problem. These comments typically refer to signal estimation. If we come to system estimation, we find that we are trying to estimate models, and we are trying to estimate models. Typically, model estimation, as we have seen, involves two things. Firstly, it is model structure estimation, or deciding on a model structure, and secondly, trying to decide the parameters of the model within that structure. Now, we have also seen, we have also made comments that a model is always an approximation of the system. So, it is not always, so the actual physical mechanisms which are at play could be much more complex than what is really required. What is required in many cases is that we are able to predict or characterize the system signal values using some computational method. So, for that we need a model which is able to let us compute that the system behavior within the operating modes that we are likely to encounter. So, for that we can, without even going into the process physics, in many cases we can simply adopt some mathematical model structure and try to find parameters within that model structure such that the input output behavior can be explained by that model structure. We really need not bother what are the physical, chemical phenomena associated with the process. So, in that sense we are trying to build, we are trying to adopt a numerical approach to the model. It is true that, I mean, sometimes the process physics and chemistry gives us important guidelines to the selection of the model structure, that is correct. But while it is so, we need not take recourse to physics and chemistry to be able to know a model structure. For example, there are, I mean, one of the very popular approaches of signal modeling is using the neural network, and it is typically used in cases where the process physics and chemistry are really very complex, sometimes unknown, and therefore we either cannot or we do not want to really look into all that physics and chemistry. So, what we say is that let us take a neural network which has a very flexible structure which can really describe or capture a lot of kinds of behavior, and then try to find out that what are the parameters in that neural network, so that my particular behavior can be faithfully modeled. So, what we are essentially doing is numerical modeling, and the big advantage that it can give us is that it can lead to a lot of simplicity in modeling, and it can also let us talk about system behavior without knowing the process physics and chemistry, and in various situations where modeling based on physical conditions would indeed have been impossible. Like in the case of, again coming back, like in the case of tool condition monitoring. In the case of tool condition monitoring, how the tool actually wears through its interaction with the job is actually an extremely complicated procedure, and there does not exist any well accepted method for actually modeling that. And there are some empirical model structures which again have been obtained basically through estimation. So, we could see that even without knowing anything about the tool job interaction procedure and the mechanics associated in it, we have been able to model it simply using a neural network. So estimation gives us a totally alternative approach to modeling, which I have called here as numerical modeling. Similarly, estimation lets us, in the same vein, I mean, estimation lets us discover patterns, you know. So, using estimation, if you are given a large volume of data, various variables, their time values, we can create a mathematical object which can very compactly represent, which can these I mean, let us say kilobytes and I mean thousands and thousands of different values, we can very compactly encode into a numerical model structure, which will be good enough for our purpose, in the sense that they will be able to explain each other's behavior using estimation. So, in that sense, it is data mining, where we are trying to discover patterns, dynamic patterns, complex dynamic patterns from large volumes of data. We are also doing knowledge extraction. So, as you can see, as we can probably reflect on at the end of the course, that this is what the techniques that we have learned throughout the semester, this is what it lets us do. It lets us, it basically provides a very elegant tool into the measuring tool, knowledge gathering tool, simply from observed behavior, and that knowledge and that information we can use for a host of purposes of decision and control. That is why this course is so important. I mean, you will find that, I mean, especially now with computers available everywhere, I mean, computers being available in all machines, the role of information in optimal operation and control is increasing, and the use of estimation technology in all these applications is becoming, I mean, almost all pervading. So, this is what we have learned. I thought that before going to review the course, I mean, how we had actually made our journey, I wanted to emphasize that point, that throughout this course, this is essentially we have learned. We have learned to design and implement a tool which will give us much more condensed, useful and high level information which is available in the measurements and which we can use for optimal operation. So that is what we have learned during the semester. Now, let us take a review. Let us just slowly or rather quickly go through just recapitulate the journey that we undertook in the course. So, we began the course in July. The first lecture was an introduction which actually introduced the estimation problem and tried to describe what in essence it is. That is what we have just done again. And then we began right at the beginning, that is, we began at probability theory, because of the fact that estimation theory typically involves basically estimation says that you can gather information in the face of uncertainty and knowledge, uncertainty and noise, right? And typically probability theoretic approach is usually adopted for describing these behaviors mathematically. So, we, without assuming any background whatever, we started right from probability theory and then went on to talk about random variables. So, these are variables which take on values, and what values they will exactly take is uncertain. So, when they are uncertain, why are they uncertain? Because again, because there are certain phenomena at play which influence the values that these variables take, which we are not interested in modeling. Either we are unable to model, or we are not interested in modeling. So, therefore, we say that these variables are random. So, we cannot exactly say what values they will take. So we try to characterize random variables, and then from random variables, obviously whenever we are talking about processing any signal or processing a system, we have to work on them either using various kinds of operators, right. So, first of all, we took a static operator, in the sense that we took functions of random variables and saw that if a random variable behaves in a certain way, then how do these functions behave? What are the behavior of the functions of them? We also saw that if there are a number of variables and each one of them behaves certain ways, then how to characterize the random behavior of this collection of variables in terms of their individual behavior. So we talked about joint density and distribution of a number of random variables. Now it turns out that we are always, everywhere it is very convenient if we can, even if we lose some accuracy, it is very convenient to compress knowledge and express some rough behavior in terms of 1 or 2 numbers. So in that sense, while these variables are actually uncertain and they can take values over a certain range, it is very convenient to define 1 or 2 numbers which will roughly explain their values and behavior. So from that sense, mean and variance are very important quantities which describe which describe 2 things. The mean is called a measure of central tendency, or that if you take 10 such variables or 10 such realizations of these variables, then what is an average behavior? So in that sense, mean is important, because by just one number you are able to characterize all the realizations up to a certain accuracy, and to what accuracy, that depends on variance, which is a measure of dispersion, right. So it says that how much does it differ from the mean. So we define these 2 very important quantities which are used in the characterization of these random variables, and then we gradually graduated towards more and more complicated objects. We looked at random vectors, which are an organized collection of random variables, and then we looked at random processes. So random variables are single values, while random processes are actually random functions, as we have seen. So from random processes, now these, just like variables, will be operated by functions. Similarly, functions of time will be operated by dynamic operators. So we have to characterize that how these functions, when they go through various processes, how their time behavior gets transformed by these processes. This is of great interest to us, and essentially, to keep things simple, we always consider linear dynamics. So then we came to see how these random processes behave when they are passed through linear systems. So if you are given the power spectral density of the input, can we calculate the power spectral density of the output? Because that is very important, because in many cases what we want is that we want to characterize the process. So we characterize the process essentially in terms, so we say that this is a process which when fed with an input of this kind will produce an output of this kind. So to be able to characterize this phrase this kind, we need to characterize these random processes and their processing through linear systems. So we did that. After that, we did solve some problems on lecture 8, and finally we reviewed some very important special topics on random processes before actually going on to an estimation problem. So we talked about the normal or the Gaussian distribution, which is very important, because especially because it has certain very interesting properties when operated through linear systems, like it retains its Gaussian character. We also talked about white noise, because white noise is, in a sense, like it's a characterization which is a counterpart of the impulse, and it leads to considerable analytical simplicity in our analysis. We also talked about ergo DCT, which is we have to talk about, in many cases it turns out that to be able to characterize average behavior, it is very inconvenient to talk about ensemble averages, because usually we do not have so many realizations of a process. So, we instead we often recourse to time averages of a single process and substitute that for ensemble averages. So, now I mean essentially when we want to do that, we have to make an assumption about ergodicity. So, we reviewed these three concepts and summarized our studies on random processes before we became ready for handling estimation problems. In lecture 10, we again looked at some further on linear signal models, especially because we found that if you want to characterize output properties with input properties through linear signal models, then there are certain kinds of linear signal models which are very convenient, which can very conveniently model a very wide class of input output behavior. So, we looked at that, and we looked at the all zero, all pole and pole zero models. And at that point of time, we considered our first real estimation problem, which is the linear mean square estimation, which says that if I am given measurements of a certain quantity as values which are sequenced over time, then using a finite sequence or an infinite sequence of these values, can I estimate another quantity? Can I do that? So, and if I can do that, can I do it using a linear model? And if I want to do it using a linear model, if I only restrict to linear models, what is the how to obtain the best estimator which gives me the minimum square error of estimation on an average over ensembles again, which means that if we do this estimation with 50, 100, 200 different signal sequences and get corresponding error sequences and compute square errors and average them, which is the value of this estimator, what are the parameters of this estimator which is going to give me the least mean square error. So, that is the minimum mean square error problem, which is well known and which essentially reduces to a Wiener filtering problem, and we obtained a solution of that using the so called normal equation. At this point, we in many cases it happens that we want to use frequency domain information, we want to do frequency domain modeling because of the fact that various complex differential equation properties in the time domain become algebraic, so that the manipulation becomes much user in the frequency domain. So, it turns out that we need to understand how to estimate what are known as autocorrelations and then take the autocorrelation in the frequency domain to get the power spectrum. So, we needed to study how to estimate autocorrelations and power spectrums and then obtain frequency domain models of systems in terms of the power spectrum of inputs and the power spectrum of outputs. And it turns out that under certain very rather mild conditions, a lot of power spectra can be actually modeled using linear pole zero models. So, with that we studied the autocorrelation and power spectrum estimation. We studied two approaches, one based on smoothing, another based on ensemble averaging, and we found out also nicely that if we are given a sequence, then these two approaches are roughly equivalent in the sense that they lead to the same kind of loss of frequency domain or time domain accuracies. So, now we are ready to explore models in the frequency domain, and since we are mostly working in in the discrete time framework, where we have, rather than having a signal, we have a sequence of sampled values. So, the frequency domain description of systems in the sample domain is a Z transform. So, we recapitulated the Z transform, and we also recapitulated a basic concept of algebra relating eigenvalues and eigenvectors, which becomes useful in many kinds of analysis of stability, innovations, etc. That was lecture 13. And in lecture 14, once we have understood our eigenvalue eigenvector concepts and how they can be used to orthogonalize a sequence, we introduced the concept of innovation. The concept of innovation is very interesting in the sense that it transforms the information which is contained in a sequence of data values into a form where the information is not really spread on each data sample. That is, each data sample brings in new information. The sum total of information remains the same as the old sequence, but now this transformed sequence, which we sometimes call an innovation sequence, every component of that sequence or every sample of that sequence brings in new information. So, that information which is not obtainable from that of any other sequence. So, this kind of compartmentalizes the information, and again lets us do analysis in a much more deep and effective manner. And then we saw that what is this innovation in the context of the linear minimum mean square estimation, which we have already studied, and found that the optimal minimum mean square, the minimum mean square estimation actually leads to the error being perpendicular to the data. So, in the sense that it becomes orthogonalized, and each of these errors actually bring us new information which we need to incorporate while we are updating our parameter coefficients. Coming from linear mean square estimation, which actually linear mean square estimation is in a sense optimal over all possible data sequences, true, because it minimizes the error over an ensemble average, that is correct. But at the same time, as we have seen, it requires knowledge of the properties of the ensemble, which may or may not be available. So, when it is not available, what we can do is we can say that, okay, I do not have the data available for the whole ensemble, but at least can I obtain the best data which is best for this data sequence. So, if we are trying to optimize the error over the whole ensemble, we have minimum mean square estimation. If we are trying to optimize the error only for the given sequence, then we are doing least square estimation, which are really very related. So, we saw that how for we actually talked about the linear minimum mean square estimation in the context of FIR models or all zero models. Then we saw that how we can estimate optimal IIR models, and we saw that actually employs the concept of innovations, the concept of pre-whitening, and a lot of other things. Having described fixed filters, how to estimate fixed filters, we went to tackle a new situation where the properties of the data may be changing over time, in which case if we employ a fixed estimator, as soon as the properties of the data change, that estimator does not remain optimal. So, in this sense, actually we cannot really compute a linear minimum mean square estimator, because the matrix R and D, that is the cross covariance and the autocovariance matrices, they actually do not exist because the data is non stationary. So, if we have non-stationary or quasi-stationary data where these ensemble properties are slowly changing, we need to also keep our filters not fixed, but slowly adapting with the data properties. So, to do that you need adaptive filters. So essentially what you try to do, as we have seen, is that you try to compute these properties, these ensemble average properties online from the data that you have available, and we looked at two different approaches. One is the steepest descent approach, and the other is the least mean square algorithm. So far we have been talking about what is known as input output model, in the sense that we assume that the measurements are the inputs to our filter and the quantity that we want to estimate is the output. But there are lots of situations where for the process that we are trying to estimate, we have some measurements. Now we want to estimate other quantities like a state, we for example, we get, again coming back to that target tracking example which we did, we are getting measurements only of position. So in that sense, since we are getting measurements of position is an output, but we are interested in knowing not only an accurate value of the position, but also of the other states of the system, that is the acceleration and the velocity. So from a set of measurements which are actually a combined expression of the states, we want to get the states. This is a very common problem and a very important problem for a large class of dynamic filtering cases, and we took that problem up and after describing the basic rules of state estimation in a deterministic framework, we looked at the Kalman filter, which is an optimal linear estimator under certain assumptions for a stochastic version of that state estimation problem. That is, when we have uncertainty in the process input, in the sense that we don't really know what the process inputs are, so we assume that the process is being excited by some random signal, and we also have uncertainties in the measurements. So in the presence of these uncertainties, how to obtain an optimal estimate of the system state is the problem of Kalman filtering. This is a very well used and well known algorithm. So we looked at it in great detail and derived the Kalman filter over two classes, lecture 18 and 19, and finally derived the Kalman filter equations from the basics, from the basic least square optimization viewpoint. We adopted that viewpoint because there are, actually, as it turns out, that as has been mentioned in the class also, that the Kalman filter can be derived in various ways under various assumptions. So we found that the least square optimization viewpoint is one of the easiest to understand, because it does not assume does not make too much assumptions about the noise statistics, and at the same time does not require a lot of knowledge about probabilistic descriptions of signals. Having derived the Kalman filter, we looked at its properties, namely two properties. First property was that, again, some algebraic orthogonality properties, that is the estimation error is orthogonal to the measurement sequence as well as to the estimate sequence. So in that sense, we have been able to, in that sense, once when the estimation error is actually orthogonal to the state estimate sequence, then it turns out that we cannot extract any further information from the measurement sequence to improve our estimates. So in that sense, the the estimate becomes optimal. So we looked at that property, and we also looked at a very nice, a very nice probabilistic property which says that under certain Gaussianness assumptions of the noise, the Kalman filter is actually a conditional mean. That is, given the measurements, that estimate is the best estimate. So we also looked at this probabilistic property of the estimator. Now, if you put the first of all, there are this is the basic Kalman filter property which has many assumptions in it, and so necessarily we have to take a look at how we can relax some of these assumptions, because in a real situation, if you want to employ the Kalman filter, I mean our context may not really satisfy all these assumptions that the Kalman filter needs. So in that case, we need to really make little modifications to the filter, and we looked at two cases. One is that the measurement noise is colored, and second, that the process noise and the measurement noise are correlated. So we saw, I mean, very simple methods by which these two cases can be tackled, and we also took a look at what happens to the Kalman filter in the steady state, or when does it become a time invariant filter, because that's very interesting, because mainly because of the fact that we are firstly we are in many cases interested to understand steady state properties which hold for long periods of time, and also because once we have a time invariant filter, it becomes so easy to analyze control loops. If you have a Kalman filter, as I have told just now, that an estimator provides feedback for what? For control or for guidance in aerospace. So here basically it constitutes the feedback transfer function. When you feedback, you actually feedback through some transfer function which is typically referred to as HS. So the estimator stands in that box which is the HS. Now, if it is a time invariant filter, then it is so much easier to analyze the behavior of the whole control loop, and so it is interesting to know under what conditions the Kalman filter becomes time invariant. So we looked at that, and finally we came to some applications. In detail we looked at a target tracking case, and we found out indeed that the Kalman filter can indeed remove a lot of noise. In fact, what was very impressive in our class to see that if we did not have the Kalman filter, and if we had a noisy noisy position measurement as we had, and we tried to differentiate that to get velocity and acceleration, it would have been completely hopeless. So that shows how cleverly the Kalman filter algorithm has been designed, because it gives us a pretty good estimate of the velocity and acceleration, and it has been widely used in many applications, one of the most important applications being the aerospace systems. We looked at the various computational issues where numerical problems can actually degrade performance. We looked at the square root filter, and we also looked at other variants of the Kalman filter like the extended Kalman filter, which is useful for nonlinear systems or for simultaneous state and parameter estimation, where the parameters of the system are simultaneously changing, and we want to estimate the parameters as we estimate the states. At this point, we have seen two important classes of signal estimation, one based on input output models and the other based on state space models. At this point, we concentrated towards system estimation, which is the second major component of our course. So we first described some basic introductory concepts like realizing that the model is after all an approximation of the system which only remains valid under certain operating conditions, certain kinds of inputs that you give, and for certain purposes. So, and we also described the setting of the system identification problem, that is, you have a set of input output data, you have sometimes you have a model structure given, and you have a model structure given, and you also have a performance criterion given, and you want to find out the best model within which fits that model structure, that is called a model set, and we want to find out the best parameters for the model within that set. So, again we began with the simplest possible model structure, that is called linear regression models. I mean, actually a lot of systems actually fit this model structure, and it has been widely used in various kinds of systems and control. And then we looked at a very simple and well used algorithm called the recursive least squares. Now, the recursive least square algorithm works in the base case, but there are a number of cases where we would like to where several variants of the algorithm can really improve performance. So, we considered some variations in the basic least square algorithm, in the sense that we considered exponential forgetting. Exponential forgetting lets us keep this rather than finding a model which is equally good over the whole time horizon. If we feel that the system is slowly time varying, then it makes sense to say that the parameter estimates which are being obtained now should best explain the data in the recent past and need not explain the old data to that good an extent. So, in that case we are what we are essentially saying is that I need to put more emphasis on the signals which are of recent past and need to explain them better, and can perhaps ignore the distant past signals to be able to make a compromise. So, that is achieved by exponential forgetting. Sometimes we would require that some parameters, suppose we are interested in the DC gains. So, we say that we want to estimate the low frequency properties of the system very accurately, and we can perhaps sacrifice the high frequency properties to an extent, in which case you have to have weighted variations of the least square. Then one of the problems of the basic least square algorithm is that it gives what is known as parameter bias, in the sense that even if the model structure is the same as that of the system, because the noise is actually correlated with the data, you are if you simulate the data using even if you simulate the data in a computer and then use the exact same model structure, you will not get back the parameters which you use for simulation. So, you are going to get a parameter bias, and this essentially occurs because the noise gets correlated with the measurement. So, there are again various ways of tackling that. One approach is to model the noise, which is very similar to the case of the correlated measurement noise case that we saw in the Kalman filter, in the sense that you have to then once you find that the noise is actually correlated, you have to model that how this correlated noise was actually generated. So, you have to model the noise generating mechanism and enhance the augment your model structure with this noise model, and then go on estimating both the system model parameters and the noise model parameters. There is another very elegant approach to remove bias, and that is the method of instrumental variables, where you actually use a signal. In certain places, rather than using the measurement vector, you use a vector which we call the instrumental variable vector, and which it has the property that it is very well correlated with the measurement, but it is highly uncorrelated with the noise. So, we are actually taking two approaches. In one case, we are trying to, including the noise model, we are trying to whiten the noise. In the other case, we rather than using the actual data or the actual measurements which are correlated with the noise, we are using a slightly different data, so that it becomes uncorrelated with the noise. I mean, the advantage is that you do not have to use a noise model, but then the disadvantage is that you have to again compute this so called instrumental variables. So I mean, if you want to get something, you always lose something. It's very difficult. I mean, it usually does not happen that to be able to, I mean, you get something without sacrificing anything else. Then we looked at some special topics on least square estimation. Number one is the condition of convergence. That's when is it guaranteed that the least square algorithm will converge. We looked at how we can identify a system in closed loop, because it may not be always possible, because there are certain problems that occur in closed loop, in the sense that typically in a closed loop the noise tends to get correlated with the measurements, because the inputs are being generated from the output. So, the output noise creeps into the inputs, and there are in certain cases, if you use very simple controllers, then you can get into what is known as a loss of identifiability if you use closed loop identification. And then we looked at various practical identification strategies. Finally, we looked at model order selection, and that is how do we know what models. I mean, the least square algorithm typically assumes a model structure. So, we saw how we can select model structures essentially iteratively, and also by looking at certain structural algebraic properties of certain data matrices, like correlation matrices, and I mean examining their ranks. We also can look at the residual, because we know that if our parameter estimates are going to be good and under the model structure, then the residuals will have certain properties of whiteness. So, if after long estimations that whiteness does not come, then we can perhaps infer that there is something wrong with the model structure itself. Go back and change the model structure, and then again go through the estimation process, and again check the residuals. So, again it is an iterative process. Finally, we saw that how, suppose we are actually given a situation where we have a practical system, and we have to connect wires, and you have to get the data, maybe using data acquisition cards, and actually write a code and do system identification. What are the various steps, what are the various issues that we have to go through before we can get a model which will be good enough for our purpose. So, we looked at the practical issues in identification. So, this kind of completed what we wanted to complete in our course, and as I have told you always that it is very important to know in a course, I mean especially towards the end of the course, as to what we have not learned, because it will always turn out that you have any course in any area, you cannot learn everything in that area. So, it's good to take a look at, very brief look at many other things which we did not get time to look at in detail. So, in the last lecture we looked at some other estimation problems which we did not really see in depth. For example, we looked at the fault detection and diagnosis problem, which is very important, especially for some safety critical and mission critical applications. We looked at multi-sensor fusion, and here it is that we looked at the tool condition monitoring example that we repeated, where using more than one sensor and using clever estimation, we can really construct what we can call a super sensor, for which we cannot have any physical device. So, we can enhance the individual properties of each sensor just by combining them and then using an estimator. We can use forecasting. Forecasting lets us look at the future and probably get prepared for it, take preparatory actions, very much used in various kinds of industries, stock markets, electric utilities, and then looked at higher, I mean a kind of estimation which is really higher than signal and system estimation, which is learning. So, and that brings us to today's lecture. So, this is what we did in the course. Essentially, I think that with what you have been told, you are very well equipped to go ahead and tackle any estimation problem that may arise in a given engineering context. So, with that I would like to close the course. It was a very pleasant experience for me. Thank you very much.